of the multiple and add to that row will become all 0, right? Okay, in that case, so it's like you know, A11, the A1n. If you another row is, for example, CA11, CA12, CA1n, AN1, ANN. If that's the case, you multiply negative C to the first row and add to the third one. Okay, then this row will become empty, right? This row will cancel out, become empty. So what you are doing is you know, you are doing is you know, you multiply 1, 1, 1, 1, 0. You multiply a C, negative C to some row here. Okay, to this let's say original matrix is A. Okay, so multiply A. Okay, you get a B, and the B will have like one row to be 0. Okay, and we know like a determinant of B will be determinant of this thing, okay, times this is E, okay, times determinant of A. And this one, okay, is a lower triangle, so this is 1. And this one, we know this is 0, okay, because 1, if you have a row to be 0, then, you know, the determinant of that matrix is 0. So obviously, determinant of A is 0. Okay? So, okay. N times N matrix is singular if and only if determinant of A is 0. Okay? So how do we show it? Okay. If if a matrix is singular, then according to the Gaussian elimination, okay, there must be a series of basic row operation that we can apply. Eventually, will lead to, you know, some at least one row at the end, you know, to be all 0, right? One row at the bottom to be all 0 at least. Okay, so you know, if that's the original matrix A, you apply the elementary row operation E1, E2, EK. Say you apply K different elementary row operations. Eventually, you get your, you know, Gaussian elimination, you know, result. Let's say that one is your B. Okay, then according to the, you know, the previous discussion, the determinant of B, okay, which is 0, obviously, because you have like some row to be 0. It's going to be a determinant EK determinant EK minus 1 determinant E1, okay, times determinant A. Okay, and we know that all these, you know, the you know, elementary matrices, okay, that corresponding to your elementary row operations, okay, they are non-zero. Okay, actually, okay, if you change two rows, it's -1. If you you know, multiply a row by a non-zero factor, then there will be, the determinant will be that factor. And if you multiply a row by a constant and add to another row, the determinant will be, the corresponding matrix for the, determinant of the corresponding matrix will be 1. So basically, this is non-zero. Non-zero. So because this is non-zero, okay, and the left-hand side is 0, and this part is non-zero, so the only thing that has to be 0 is determinant A. Right? Okay, so that's pretty much about it. Okay. So the theorem that A and B be n times n matrix, then we have determinant AB equal to determinant A times determinant B. Okay, so eventually we have this theorem, okay, that makes the determinant computation, it could simplify determinant computation. Okay, so how do we argue that? Okay, how do we prove that? First, okay, if at least one of them is singular, okay, because a matrix could be either singular or non-singular, right? If it's singular, then the determinant. In previous discussion, we know if you multiply, if determinant A or B is singular, okay, the multiple of AB will also be singular. Previous we have proved that, okay, and in the previous discussion we know if AB is singular, determinant of AB is 0, right? And if one of them is singular, we know at least one of them will be 0, right? So the whole thing will be 0. So if either A or B is singular, then this equation holds, right? This equation is true. If both are non-singular, okay, then we can convert, okay, these matrices into the a list of, because eventually we can use if a matrix is non-singular, we can use the elementary row operation and eventually make the matrix into identity matrix, right? So eventually it's going to be like this. I equal to EK minus 1 EK E2 E1 times your A through your all these elementary row operations. Eventually A can be converted into identity matrix. Okay, that's what we meant by A is non-singular. Okay, and similarly, okay, when B is non-singular, so we have the same thing. Okay, and remember that, okay, all these identity matrices, all these matrices that corresponding to the elementary row operations, they are invertible, right? They are invertible. So, we can actually write them into, what should I say? E1 negative 1, E2 negative 1, blah, 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 EK negative 1. And the B equal to similarly, okay, they are different. Oh, I probably should use prime here. Okay, E prime 1, okay, negative 1. E prime, E2 prime, negative 1. E K prime, okay, prime, negative 1. I can write them into like this. Okay, basically you just multiply like the inverse of EK. Okay, you get rid of this, and this one become EK minus 1. And you multiply EK minus 1 inverse. So on the left-hand side, so you can become EK minus 1. You get rid of this, and so on. So eventually you get like, you know, A equal to this one, B equal to this one. Okay, and then the determinant. So A times B. So A times B is pretty much, you know. And, oh, by the way, you also need to understand the inverse of elementary matrix is also an elementary matrix, right? Because it exchanges two rows. What is the inverse of it? It changes again, right? Right? So that's, again, that's an elementary operation, right? Elementary row operation. I mean, multiply a row by constant C, non-zero constant C. Well, how to reverse it? Multiply the same row by 1 over C, right? Okay? That's obviously 1 over C is also a constant, and it's also non-zero, right? Okay? And if you multiply a row by constant C and add to it another row, what is the inverse of that? Multiply original row by negative constant C, add to that row to cancel out that, right? So basically all these inverse, okay, are also elementary row operations too, right? Okay, just want you to be aware of that. So A times B actually is like a multiple of like a lot of like elementary row operation matrices. Okay, so determinant of A times B equal to determinant of E1 make 1, determinant E2 negative 1, determinant EK negative 1 times E1 prime negative 1, E2 prime negative 1, EK prime negative 1. Okay, and each of them can be, you know, written like separately. So it's going to be determinant of A, determinant of B. Okay? So, we are almost done. The Cramer's rule. Okay, I think like if we can finish Cramer's rule today, I'll be very happy. Okay, I'll be very happy because we are pretty much done with like a determinant. Okay. So before we discuss Cramer's rule, the first thing we need to discuss is the adjoint matrices. Okay. What is adjoint matrices? Okay. Let A be an n times n matrix. The adjoint matrix of A, okay, denoted by ADJ A, is an n times n matrix given by this one. ADJ A equal to this thing. So the cofactor of every corresponding, you know, A's elements appear, you know, over there. But there's a small twist here. Okay, it's actually transpose, by the way. Okay, because you know C21 happens like at the location, like a transpose location, right? So this one I want you to be aware of that. Okay. Other than that, everything like it should be very easy to remember. Okay, that's the joint matrix of matrix A, and also want you to be. I also want to remind you. Okay, every Cij is a number, is a value, right? 所有这些所谓的这个Cij， 它都是一个一个数值嘛，对不对？因为我们在计算这个 determinant 的时候，中间用到的，它们都是数值。Okay, so they are not really like a matrix. Okay, they are not matrix. Okay. So since AI1 Cj1 plus AI2 Cj2 blah 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 plus AIN Cjn equal to delta Ij determine A. We know that. So AdJ, A times AdJA, Ij, okay, if we consider the ith row, j's column, it's going to be exactly that. Okay, that's going to be delta Ij determinant A. So, in other words, let me get rid of this. So this is just a clever way of, denoting like the inverse. Okay, so A times AdJA it's actually going to be every row, every column, it's going to be delta. For example, this one is 1, 1. This is determinant A. This is delta. I need some more space. Delta 1, 2. Determinant A. Delta 1n determinant A. This is delta 2, 1 determinant A. Delta 2, 2 determinant A. Delta 2n determinant A. Delta n1 determinant A. Delta nn determinant A. That's the result of this like matrix multiplication. Okay, according to the the definition of this delta Ij determinant A. Okay, so, and I just want you to be aware, delta, when I equal to j, that's 1. When I, j are different, then delta Ij is 0, right? So obviously, in that case, all the lower triangle except the, an upper triangle, except like the diagonal terms are 0. This is 0. This one is 0. The only thing left is the diagonal. But diagonal, because 1, 1, 2, 2, I mean, this delta 1, 1, delta 2, 2, they are all 0. So they are all 1. So we have So far so good, right? So if we define a adjoint matrix like that, then A times adjoint matrix is going to be like this. And because all these terms are the same, all these terms are the same, so we can write it into like a like this, right? Is that okay? So this one equal to this. By the way, remember this is a number, right? This is a number, right? So, in other words, A times we have this, right? We have this, right? Right? So because A times this thing equal to I, so this thing is A inverse. Okay, so this also makes sense because when determinant, the A is singular, the determinant of A is 0, right? And the inverse, when A is singular, there is no inverse of A, right? So this is obvious, makes sense, right? This obviously makes sense. Okay? So the last one, Cramer's rule, okay? That A be a n times n non-singular matrix. Also, we already know it's non-singular, okay? And the B is a vector, okay, n-dimension vector. That AI be the matrix obtained by replacing the ith column of A by B. If X is the solution to AX equal to B, then Xi equal to the determinant of AI divided by determinant of A. This is what we call Cramer's rule. Okay, we actually do this like I think I learned this when I was in junior high school, but of course at that time when the teacher told us this, he or she will not explain what this really means. Okay， 就是我们小时候学的时候，这个被拿来当公式用了。OK， 但是当然小时候学，他不会跟你讲这叫 Cramer's rule。OK， 因为小时候学公式都不会讲英文嘛，对不对？那小时候学这个，他也不会跟你解释它后面的原因哦。但是就是说，这边的意思是说，譬如说，你有一个AX 等于 B，OK， 假设你的 A 长得像这样子 ，A11、A12 点点 A1 A21、A22。A2n 点点 AN1 AN2 ANN。他是说，譬如说你的 x1，就是你的解啊，如果解存在，你的 x1 就是你把这个 determinant 哦，就是把这个譬如说我们讲 x1 好了 ，x1 它的解就是这个 determinant of a， 这不用什么好解释的，就是你这个 a 放下面，上面就是 determinant， 你把第一个 row 啊，对不起，第一个 column 换成那个你的 b 啊，就是这个 b， 这个 b 当然也是一个这 b1 b2 点点到 bn 嘛，你把这个 column 放进去 b1 点点到 bn， 然后这边有 a12 然后点点到 an2 OK， 然后点点 a1n 点点到 ann， 这个矩阵的 determinant 放在分子啊 ，a 的这个矩阵放分母，这样这是你拿到 x1， 那 x2 的话，你就是把这个 b 哦放在这个第二 column 对，第二 column， 然后以此类推这样子，你就可以把 x1、x2、x3 这样都算出来，这叫 Cramer's rule。OK， 为什么？因为我们知道说这个矩阵哦，这个东西是它的那个对 A 这个 A 矩阵来讲，这个是它反矩阵嘛，对不对？是它反矩阵，所以呢，你看哦，这个 xi 哦是这个反矩 A 的 inverse， 因为 ax 等于 b 嘛，所以呢 x 就会等于 a 负1 b， 对不对？所以你把左边都乘上 a 负1。那 a 负1我们已经知道了嘛，它就是这个 determinant a 分之 OK 1乘上这个 adja， 对不对？然后再乘上 b， 这是你的 x 哦，这是你的 x。那你如果说你要知道第 i 项，那你就看它的第 i 项，它的第 xi 就是看这个东西的第 i 项。那你把这个东西整理一下 ，OK， 它其实就会长成这个样子。OK， 长成这个样子的话，你这个东西你可以把它表示成这样子，表示成这个样子，就是这下面还是不动啊，这边下面还是不动，是分子，把它表示成这个第这个，因为我们是第 i 项嘛，这边第 i 个 column。变成 B， 其他就变成还是原来的这个 matrix， 那就变成这样子。所以这就是 Cramer's rule，OK， 这就是 Cramer's rule。那当然 Cramer's rule， 我们讲到这边就这个章就结束了。其实你们可以把这个东西 apply 在我们前面的。那个第一章不是有很多那个线性方程式吗？譬如有一些3乘3的方程式，那你可以试试看 ，OK， 用 Cramer's rule 去解它。当然前提是它是可解的哦，它是可解的，而且不是有无限多解的那种情况。OK， 就是不可解或者无限多解，基本上它都是 singular，OK， 都是 singular。那 singular 就是没有反曲阵哦，没有反曲阵的话，当然。你这个分母就是0哦，所以它这个就不能这样用哦。所以这边的 Cramer's rule 很重要一点 ，A 必须要是 non-singular， 所以它就只会有一组解，它只会有一组解。OK， 那所以你们可以用这个去看说，哎，这个东西去解那个前面的那个，譬如说3乘3的方程组啊，有没有是对的 ？OK。但是当然，这边也要老实跟大家讲，你这个计算不会比较简单哦，因为你算这个每一个这个去算 determinant a， 假设3乘3好了，算这 determinant a 上面也是一个3乘3，下面也是一个3乘3，那 我知道分母都一样啦，可是上面每次都不一样嘛，所以你至少假设是一个，就是你的那个3乘3，假设你有3个变数 x1、x2、x3 好了，等于说你分母算1次，分子算3次，你要算4个 determinant 啊，说不定，所以老实讲，这个应该不会比就是你直接去解它来得快 ，OK， 只不过你们可以试试看练习一下，因为毕竟这个等于说是你有可能是可以把它扔到电脑让电脑帮你做的，对不对？就是相对起来，就是这个是一个，毕竟它是一个公式嘛，对，所以讲到这边，大概这一章讲到这边哦，那我们还剩下5分钟哦，但是时间其实也不太够，再开始讲下一章。我们今天就上到这边，把这一章结束。那同学今天有什么问题吗？如果没有问题，我们下一章就会开始讲那个 vector space，OK， 会讲 vector space。那下一个礼拜讲到的地方就是我们期中考的地方，好不好 ？OK， 那也是我会下一次上课完了以后，我会把练习题share给大家。然后当然，这里要跟大家讲哦，期中考跟小考比起来，严格讲起来，小考会就是说那个会比较难，但是会从勾的题目里面，就是说找类似的题目，就算是不是完全，就是我的意思是说，我那时候讲说2/3从里面出来，1/3从那个出来，目前我都还没有出自己的题目，但就算我现在出自己的题目，也会出类似的题目。OK， 那是小考就是 quiz， 那期中考、期末考就会比较是操作型的，可能会比较简单，可能，但是也就是说有一部分会是也是还是证明，就是至少不会是像小考比较多是证明啊，了解我意思，可以吗 ？OK， 这边也先跟大家讲一下。那讲到这边有什么问题吗？如果没有问题的话，我们今天就上到这边，好不好？好，谢谢大家。